Let me show you how to use MATLAB to calculate the Fourier transform of the use functions. First, let's look at the rectangular path function. So in MATLAB, there is a more general definition for the rectangular path. So you can define the rectangular path function in this way. This is A, B, which means this T, then between A and B, the function value is 1. Then the unit gain function is just a special case of this. So when A is -1, B is +1. So when this is scaled, when A is -half and B is -half. So when this is scaled by tau, so A will be -tau/2, B will be tau/2. So first, let's define symbols A, B, T, W, W0, and tau. Let's define the rectangular path function with parameterized by A, B, and T. Then the Fourier transform of the rectangular path is this one. So negative sine n omega plus cosine A omega I over omega plus sine B omega plus cosine B omega I over omega. Now let's substitute A to -tau/2 and B to tau/2. Then let's simplify the result. See here, so this is the result. So we can write it in the form of a think function. So let's do this by divide 2 on both the numerator and denominator. Then we have sine tau W/2, then omega/2. Then let's multiply tau on both the numerator and denominator. So therefore we have tau sine tau W/2, then over tau W/2. And we know, so this is the sinc function. So SINC tau W/2. Okay. Then this result is exactly the same with the one I showed you in the slides. Then let's continue to calculate the Fourier transform of the unit impulse function. Then is 1. The Fourier transform of the unit impulse function is 1. Now let's calculate the inverse Fourier transform of the unit impulse function in the frequency domain omega. So it is 1/2 pi. The inverse Fourier transform of the unit impulse function in the time domain, okay, from frequency domain to time domain is 1/2 pi. Now let's calculate the inverse Fourier transform of the impulse function delayed by omega0. We know we can use the frequency shifting property So when a signal is shaped in frequency domain by omega 0, then in the time domain, it just multiply it by exponential j omega 0 t. You see this result is just multiplying exponential j omega 0 t. Now let's calculate the Fourier transform of the cosine function. So this is even more general form than the one we have like a cosine bt. Now we have so a times cosine b times t. Then its Fourier transform is pi a times delta b plus omega plus delta b minus omega. It is also the same with the one we calculated in the slice. Okay? In the slice, so the a is just 0. So a is 1, sorry, a is 1. Okay. Then we have delta w plus b, then plus, because delta function is symmetric, so b w minus b. Now let's calculate the unit step function. So the unit step function in MATLAB, you can use the Heaviside function to define the unit step function. Then let's calculate the Fourier transform of the unit step function. It's pi delta omega minus I over omega. The one I showed you in the slides, it is pi delta omega plus 1 over j omega. It is the same, so we can say it's pi delta omega. So if we multiply, so it's the I of j on both numerator and denominator. Okay, so this is so -1, then we have pi delta omega, then +1 I omega. It is the same. Now let's calculate the Fourier transform of the signal function. So when t is positive, the function value is 1. When t is negative, the function value is -1. It will be -2i over omega. This is also the same with the one I showed you in the slides. So it is 2 over j omega. We can show that the same. Okay? If we multiply both numerator and denominator by I, either I or j, then this is -1. Okay, I forgot the omega here. So it'll be so -1 times -2 will be 2 IW, either I or j. Okay? It is the same.